The Cambria Ironworks boardroom erupts in laughter. Robert Woolston Hunt stands before them, holding blueprints for a Bessemer converter with walls so thin, the veteran steel men call it a suicide machine. They have been pouring steel for decades with converters built like fortresses. This upstart engineer wants to strip away half the protection. Within 5 years, most of them would be bankrupt, and Hunt's paper-thin heresy would become the only way to survive. The tyranny of thick steel. The Bessemer converter was supposed to be the miracle that made steel cheap. Before 1856, steel was a boutique material, expensive enough that most of the world built with iron. Then Henry Bessemer figured out how to blow air through molten pig iron, burning out the impurities in minutes rather than hours. It was alchemy at industrial scale. A tornado of flame and sparks turned cheap iron into strong steel faster than any process in history. But the miracle came with a brutal price. The Bessemer converter was a violent machine. Inside that pear-shaped vessel, the chemical reaction reached temperatures above 3,000 degrees Fahrenheit. The molten metal churned like an angry ocean. The air blast created pressure that wanted to tear the container apart. The acidic slag ate through any material it touched. It was controlled chaos, and every steelmaker knew that the only defense against this inferno was mass. The standard American Bessemer converter in the 1870s featured walls made of fire brick and silica, backed by thick iron plates, wrapped in iron bands, and often reinforced with additional external bracing. The refractory lining alone measured 2 feet thick in many installations. The entire structure weighed hundreds of tons. The vessel looked less like a piece of industrial equipment and more like a medieval fortress designed to contain a dragon. This thickness was dogma. Every steelman who had survived the early years of Bessemer production had learned the same lesson through painful experience. When you tried to economize on refractory thickness, the converter failed catastrophically. The lining would erode through, and molten steel would breach the outer shell. The result was not just lost production, it was death. Molten steel pouring onto the floor of a steelworks created explosions when it hit water, fires when it hit combustible materials, and instant fatalities when it hit human beings. The veterans of the industry wore their thick converters like armor. They pointed to the scars on the factory floor where thin-walled experiments had failed. They calculated the cost of a catastrophic breach, not just in dollars, but in lives. The consensus was absolute. You built your Bessemer converter thick, or you built coffins for your workers. This created a vicious economic cycle. The thick refractory lining was expensive to build and expensive to maintain. After every heat, after every batch of steel, the lining degraded. The slag ate it away bit by bit. Eventually, the converter had to be taken offline for relining, a process that took days and cost thousands of dollars. The thicker the lining, the longer this took and the more material you needed. But the real cost was hidden in the physics. All that refractory mass was a thermal sponge. Every time you started a heat, you had to bring hundreds of tons of cold brick up to operating temperature before you could make steel. That heat came from the molten iron itself. The metal cooled as it heated the vessel. This meant you needed hotter starting temperatures, which meant more fuel in the blast furnaces. You were burning coal to heat brick that existed only to protect you from the heat you were creating. The established steelmakers accepted this as the fundamental equation of Bessemer production. The safety and durability of thick walls justified the inefficiency. Anyone who questioned this arrangement was questioning the accumulated wisdom of an entire generation of steelmakers who had built their fortunes on this technology. The thick-walled Bessemer converter was not just engineering. It was scripture, and Robert Woolston Hunt was about to become a heretic. The man who saw waste. Robert Woolston Hunt was born in 1838 in Northumberland County, Pennsylvania, into a world where iron was still king and steel was a curiosity. His father operated an iron furnace, so Hunt grew up surrounded by the rhythm of blast furnaces and the smell of molten metal. Unlike most ironmasters who learned the trade through tradition and apprenticeship, Hunt went to college. He graduated from the Rensselaer Polytechnic Institute in 1859 with a degree in civil engineering. This made him part of a new generation, men who understood metallurgy through chemistry and physics, rather than just folklore and experience. He could look at a blast furnace and see thermodynamics. He could examine a Bessemer converter and calculate heat transfer rates. This analytical mindset would prove crucial. Hunt spent his early career moving through the iron and steel industry, working for various companies, learning every aspect of production. He was not content to simply operate existing systems. He wanted to understand why they worked, and more importantly, why they wasted so much energy and material. By the 1870s, he had developed a reputation as a troubleshooter, someone who could diagnose problems that stumped traditional ironmasters. His breakthrough insight came from an unlikely source, watching a failed converter. In 1876, Hunt witnessed a catastrophic lining failure at a steel works. The standard response would have been to rebuild with even thicker walls. But Hunt did something different. He studied the failure pattern. He measured the temperature gradients through the failed refractory. He calculated how much of that massive lining had actually been eroded by the slag and how much had simply been dead weight, thermal mass that served no protective function. The numbers shocked him. The erosion penetrated less than 1 foot into the 2-foot thick lining in most places. The outer half of the refractory had never been touched by slag. It existed only to insulate the working face and to provide structural mass. But that mass was consuming enormous amounts of heat energy. Hunt realized he was looking at a system designed by fear rather than physics. The insight crystallized into a heretical question. What if you could maintain the working face at the proper thickness, but eliminate the excess mass? What if you could build a converter that was thin enough to minimize heat loss but strong enough to contain the reaction? Traditional steelmakers would say it was impossible. The thermal shock would crack a thin lining. The mechanical stress would tear it apart. The erosion would burn through in hours. Hunt believed they were wrong. He had seen how modern refractory chemistry was evolving. Better materials could handle thermal shock more effectively than the crude bricks of the 1860s. Improved bonding agents could create tighter, more erosion-resistant linings. Most importantly, a thinner lining would come up to temperature faster, reducing thermal stress during startup. The thick lining that was supposed to protect the converter was actually killing it through thermal cycling. But Hunt understood that theory meant nothing in the steel industry. Veteran ironmasters did not care about calculations. They cared about tons of steel per day and dollars per ton. He needed to prove his concept in the only language the industry respected, production numbers. He needed someone willing to bet their steelworks on his paper-thin revolution. That opportunity came from an unlikely source, a company desperate enough to try anything. The paper-thin heresy. The Troy Steel Works in upstate New York was not a giant of the industry. It was a small operation struggling to compete against the massive integrated mills of Pittsburgh and Chicago. In 1879, they were losing money on every heat. Their thick-walled Bessemer converters were reliable but slow and expensive to operate. They needed an edge, something that would lower their costs enough to undercut the big players. When Hunt approached them with his thin-walled converter design, they were desperate enough to listen. Hunt's proposal was radical in its simplicity. He would reduce the refractory lining thickness from the standard 2 feet to approximately 1 foot. This would cut the material cost in half and dramatically reduce the thermal mass. But the real innovation was in how he achieved this reduction without sacrificing durability. Hunt had developed a new refractory formula using higher quality silica and better binding agents. This material could withstand the same erosion as the old thick linings, but in a thinner cross-section. The innovation was not just less material, it was better material. The physics of the thin-walled converter were elegant. By reducing thermal mass, the lining heated up faster during startup. That meant less heat was stolen from the molten iron. The metal stayed hotter throughout the blow, and the chemical reactions proceeded more efficiently. The converter could process a heat faster because it wasted less time fighting thermal inertia. The thinner walls also meant less surface area to radiate heat, so less energy was lost to the environment between heats. Hunt also redesigned the mechanical structure. The traditional converter used the thick refractory as structural support. Hunt's design used a steel shell with carefully engineered supports, treating the refractory purely as a consumable lining rather than a structural element. This allowed him to use thinner, higher quality refractory materials that would have been too fragile in a traditional load-bearing application. The construction of the first thin-walled converter took place over the winter of 1879 to 1880. The Troy Steel Works shut down one of their old converters and rebuilt it according to Hunt's specifications. The steelworkers who did the installation thought they were building a death trap. The refractory walls looked impossibly thin compared to what they were used to. Some refused to work on the project, convinced it would explode on first firing. Hunt supervised every detail. He personally inspected the quality of the refractory bricks. He calculated the exact spacing of the steel reinforcement bands. He specified the startup procedure that would bring the lining up to temperature gradually to prevent thermal shock. He was betting his reputation on this machine. If it failed catastrophically, he would never work in the steel industry again. The first firing happened on a cold March morning in 1880. The crew loaded the converter with molten pig iron from the blast furnace. Hunt ordered the air blast started slowly, much more gradually than the standard procedure. He wanted to give the thin lining time to thermally stabilize. The steel workers stood at a distance, ready to run if the vessel breached. The converter roared to life. The flames shot up through the mouth, white-hot and violent. The vessel trembled with the force of the air blast, but the thin walls held. Hunt monitored the exterior temperature with his hand, feeling for hot spots that would indicate a breakthrough. The surface was warm, but not dangerously hot. The thin lining was working exactly as he had calculated. The refractory heated through quickly and then stabilized. The heat completed in 13 minutes, 3 minutes faster than the Troy Works had ever achieved. The crew tilted the converter and poured the steel. It flowed bright and clean. The quality was identical to steel from the thick-walled converters. The result made one thing clear: the advantage of efficiency over brute material mass. But the economics were different. The fuel consumption was noticeably lower. The converter was ready for the next heat immediately, with no waiting for the thermal mass to stabilize. Hunt ran the thin-walled converter for a week before declaring victory. In that time, it completed 47 heats without a single lining failure. The fuel savings were approximately 15% compared to the old converter. The faster cycle time meant they could produce more steel per day with the same equipment. The thin lining, which everyone had assumed would erode faster, actually lasted longer because it experienced less thermal shock. The numbers were undeniable. Hunt's paper-thin converter was not just different, it was superior in every measurable way. He had broken the fundamental equation of Bessemer production. You did not need thick walls to be safe. You needed better materials and better engineering. The question was whether the industry would accept this heresy or whether they would double down on the old faith. The answer came faster than Hunt expected, delivered with laughter and contempt. The laughter of giants. Word of Hunt's thin-walled converter spread through the steel industry like a rumor of a circus act. The initial reaction from the major producers was not concern, but amusement. Andrew Carnegie's chief engineer reportedly called it a paper doll for playing pretend steelmaking. The superintendent at the Edgar Thomson Works in Pittsburgh dismissed it as a trick that might work for a few weeks before catastrophic failure killed everyone in the building. The mockery had a specific tone. These were not technical objections. These were the reflexive sneers of established power confronting a challenge to their expertise. The men who ran the great steel works of Pennsylvania and Ohio had built their reputations on thick-walled converters. They had survived the brutal early years of Bessemer production, when thin experimental designs had failed spectacularly. They wore their scars and their debt as proof that only their methods worked. The criticism focused on several supposedly obvious failures. First, the thin lining could not possibly withstand the mechanical stress of the air blast. Second, Erosion would accelerate catastrophically once the lining wore down even slightly. Third, thermal cycling would crack the thin refractory within days. Fourth, and most damning, even if it worked for small batches, it could never scale to the massive converters used by the major producers. What the giants missed was that their objections were based on old refractory technology. Hunt's innovation was not just about thickness, it was about material science. The new silica formulations he used were fundamentally superior to the crude bricks of the 1860s. But the established producers did not want to hear about chemistry. They wanted to dismiss the threat as quickly as possible. The trade publications played into this narrative. Articles about Hunt's converter carried titles like "The Thin Wall Experiment" and "Troy's Gamble." The tone suggested that Hunt was either naive or reckless, that he was risking lives to shave a few dollars off production costs. The implicit message was clear. Real steel men built thick converters. This thin wall nonsense was for amateurs and gamblers. Hunt faced this wave of ridicule with strategic silence. He did not engage in public debates or write defensive articles. Instead, he did something far more threatening. He licensed his design to other small steelworks that were desperate to compete with the giants. Throughout 1880 and 1881, thin-walled converters appeared at facilities in Troy, Harrisburg, and Cleveland. Each installation proved the same: economics, lower fuel costs, faster cycle times, longer lining life. The laughter began to sound nervous. The major producers watched their smaller competitors suddenly become more profitable. The price of steel was under constant pressure, and the margins were thin. A 15% reduction in fuel costs was not trivial. It was the difference between profit and loss for many operations. The thin-walled converter was not failing. It was winning. By 1882, Carnegie Steel could no longer ignore the data. They quietly commissioned an internal study to evaluate Hunt's design. The report came back with troubling conclusions. The thin-walled converter was viable at scale. The fuel savings were real. The faster cycle times were real. Most devastatingly, the linings were lasting as long or longer than traditional thick walls. Carnegie's engineers recommended immediate adoption. But Carnegie himself hesitated. The company had millions of dollars invested in their existing converter infrastructure. Admitting that Hunt was right meant admitting they had been wastefully wrong for years. It meant writing off capital investments before they had fully depreciated. It meant a painful transition period while they rebuilt their converters. Carnegie was a man who understood efficiency, but he was also a man who hated admitting mistakes. This hesitation proved fatal for some of Carnegie's smaller competitors. While the giant debated, other steelmakers committed fully to Hunt's design. They rebuilt their converters with thin walls. They slashed their production costs, and they began undercutting Carnegie on price. The competitive pressure intensified. The question was no longer whether the thin-walled converter worked. The question was whether you would adopt it fast enough to survive. The arithmetic of destruction. The economics of Hunt's thin-walled converter created a brutal selection pressure that the traditional steelmakers could not escape. The numbers were simple enough that any bookkeeper could understand them, and devastating enough that boardrooms across Pennsylvania began to panic. A standard thick-walled Bessemer converter in 1880 cost approximately $8,000 to reline. The process required shutting down the converter for 4 to 5 days, tearing out the old refractory and building up the new lining brick by brick. During this downtime, the converter produced nothing, while the workers still needed to be paid. For a large steelworks running multiple converters, this meant constant rotation of shutdowns, always sacrificing production capacity to maintenance. Hunt's thin-walled converter cut the relining cost to approximately $4,000 and reduced the downtime to 2 days. This was not because the lining lasted longer, although in practice it often did. It was because there was simply less material to replace. Half the bricks, half the labor, half the time. The arithmetic was inescapable, but the real destruction came from the operational savings. The fuel cost reduction of 15% sounds modest until you calculate it across a year of continuous production. A typical Bessemer steel works in the early 1880s consumed approximately 40,000 tons of coal per year, to fire its blast furnaces and heat its converters. 15% of that was 6,000 tons of coal. At $3 per ton, that was $18,000 in annual savings from fuel alone. Add the faster cycle times. A thick-walled converter averaged 15 heats per day. Hunt's thin-walled design could complete 17 heats in the same 24 hours. That 13% increase in throughput meant a steelworks could produce more tons of steel with the same equipment, the same building, and almost the same labor force. Capital efficiency improved dramatically. The cumulative impact was a cost reduction of approximately $2 per ton of steel produced. In an industry where the typical selling price was $28 per ton and profit margins were often less than 10%, a $2 advantage was not incremental. It was existential. Hunt's converter turned marginal operations into profitable ones and turned profitable operations into cash-generating machines. The small steel works that adopted Hunt's technology first had a window of opportunity to exploit this advantage before the giants caught on. They used the cost savings to undercut prices in their regional markets. The Troy Steel Works, which had been barely surviving in 1879, was reporting healthy profits by 1882. Their thin-walled converters gave them a cost structure that the nearby thick-walled competitors could not match. The major producers watched this unfold with growing alarm. Carnegie Steel finally committed to thin-walled converters in 1883, beginning a massive retrofit of their facilities, but the conversion took time. Each converter had to be taken offline, gutted, and rebuilt. During the transition, Carnegie was running a mixed fleet, some converters operating at the old high costs, some at the new low costs. This created internal chaos as the company tried to price steel based on a constantly shifting cost structure. Smaller companies that could not afford the conversion found themselves in an impossible position. They could not compete on price with the thin-walled operations, but they could not afford to shut down for the weeks it would take to convert their equipment. They were trapped in a slow death spiral. Sales declined because their prices were too high. Revenue fell, making conversion even less affordable. The gap widened every month. The Pennsylvania Steelworks that had laughed at Hunt's paper-thin converter in 1881 declared bankruptcy in 1884. Their thick-walled converters, which had seemed so solid and reliable, had become anchors dragging them to the bottom. The owners blamed unfair competition, claimed predatory pricing, and demanded tariff protection. But the mathematics did not care about their complaints. They had made steel the expensive way, and the market punished them for it. By 1885, the conversion was essentially complete across the industry. Every major steel producer had adopted Hunt's thin-walled design or some variation of it. The thick-walled Bessemer converter, which had seemed eternal just 5 years earlier, was extinct. The transition happened faster than almost any technological shift in industrial history because the economic pressure was absolute. Adapt or die was not a metaphor. It was a balance sheet. The bankruptcy wave. The transformation of the American steel industry between 1880 and 1886 created a landscape of industrial corpses. The companies that failed were not weak or poorly managed. Many had been profitable for decades. Their crime was commitment to the old way, the thick-walled faith that had served them so well for so long. The first wave of bankruptcies hit the small, independent steelworks that lacked the capital to convert their equipment. These were family operations, often regional suppliers that had carved out comfortable niches in local markets. They had invested their fortunes in thick-walled converters in the 1870s, believing they were building assets that would last for decades. By 1884, those assets were worthless. The Harrisburg Iron and Steel Company collapsed in the spring of 1884. They had seen Hunt's thin-walled converters in operation at nearby competitors. They had run the numbers and knew they needed to convert. But the company had taken on debt to expand in 1882, believing that scale would protect them from competition. That debt consumed all their available capital. When they approached banks for conversion loans, they were rejected. The banks understood that lending money to a company with obsolete equipment was throwing good money after bad. Harrisburg declared bankruptcy with 1,200 workers thrown out of their jobs. The Johnstown Steel Works tried a different strategy. They cut wages and stretched out payment terms to suppliers, desperately trying to lower costs enough to compete without converting their equipment. This created a death spiral. Skilled workers left for better-paying jobs at converted plants. Suppliers demanded cash up front, choking off the supply of raw materials. Quality suffered as corners were cut. By the time Johnstown finally committed to conversion in 1885, it was too late. They had alienated their workers, their suppliers, and their customers. The company liquidated in 1886. The regional impact was devastating. Small steel towns built around a single works found themselves facing economic collapse. The workers had skills in steel production, but those skills were suddenly obsolete if the local plant had not converted. The thick-walled converter operator understood heat management for a massive refractory mass. That knowledge was useless in a thin-walled plant. Entire communities had to choose between following the industry to converted facilities or abandoning steelmaking entirely. Even some larger companies struggled with the transition. The Pacific Rolling Mills in San Francisco had been the dominant steel producer on the West Coast. They had invested heavily in thick-walled converter technology in the late 1870s, building what was then considered a state-of-the-art facility. By 1883, that facility was a liability. The company attempted a partial conversion, rebuilding one converter while keeping 3 others running in the old configuration. This half measure satisfied no one. They could not compete with fully converted Eastern plants on price, and the operational complexity of running mixed technology created constant problems. Pacific Rolling Mills declared bankruptcy in 1885, with its assets purchased by a consortium that immediately converted all converters to Hunt's thin-walled design. The bankruptcy wave did more than destroy individual companies. It fundamentally restructured the industry. The steelmaking sector had been relatively fragmented in the 1870s, with dozens of independent companies operating across the country. The thin-walled converter crisis accelerated consolidation. The survivors were either companies large enough to afford rapid conversion, like Carnegie Steel, or small operations nimble enough to convert quickly before their capital was exhausted. Hunt himself profited enormously from this chaos. He held patents on specific aspects of his thin-walled design, and every company that converted needed a license. He also offered consulting services, helping companies engineer their conversions and avoid the failures that had plagued early adopters. By 1886, Robert Woolston Hunt had transformed from a respected engineer into one of the wealthiest men in the steel industry. His fortune was built on the wreckage of the companies that had laughed at his paper-thin converter. The psychological impact on the industry was profound. The generation of steel men who had built the thick-walled plants learned a brutal lesson. Technical expertise based on old assumptions was worthless when the assumptions changed. The confidence they had felt in their methods, the certainty that had come from decades of success, had blinded them to a better way. The thin-walled converter proved that in industrial competition, there is no such thing as good enough. There is only better or bankrupt. The thin-walled Bessemer converter that destroyed so many companies in the 1880s became the foundation of American steel dominance in the 20th century. Hunt's insight that efficiency came from eliminating unnecessary mass rather than adding protective bulk became a governing principle far beyond steelmaking. The modern world is built on systems that do more with less, that substitute engineering precision for brute force materials. The direct descendants of Hunt's design remained in operation until the Bessemer process itself became obsolete in the mid-20th century, replaced by the basic oxygen furnace. But the principle survived. Every modern metallurgical vessel, from electric arc furnaces to continuous casting tundiches, uses thin refractory linings, optimized for thermal efficiency rather than thick walls built from fear. The paper-thin heresy became the only way anyone builds. The bankruptcy wave of the 1880s taught the industrial world a lesson that echoes through every disruption since. The established players, the giants who seem invincible, are often the most vulnerable to fundamental innovation. Their size is not protection. Their experience is not wisdom, if that experience is based on old assumptions. The thick-walled converter companies failed not because they were stupid, but because they could not believe that everything they knew was wrong. Hunt's legacy is the arithmetic of destruction, the recognition that in industrial competition, a $2 per ton cost advantage is not a minor edge. It is an existential threat that will bankrupt giants and crown new kings. We live in that world still, where efficiency is the only law that matters, and where the laughter of the established is often the first sign that their era is ending.